Welcome to lecture 19 of electromagnetic field and waves. I'll just briefly go over what we did last time. So this of course is lecture 19. In lecture 18, we looked at three things. Primarily, we looked at energy transported by electromagnetic radiation. Furthermore, the next thing we explored was how do electromagnetic waves behave in a linear dielectric. And I want you to go back and see how we wrote down a more convenient form of the Maxwell equations, and then using those and using the fact that when we for our linear dielectric we assume that we have no free charges within this dielectric and we have no free currents. And so based on this we then further reduced our Maxwell equations and we constructed wave equations, and we saw that our wave equations were exactly the same as the vacuum wave equations, with the only difference being in the velocity of the EM waves. And the third thing that we did was we looked at polarization, and so we looked at the polarization properties of electromagnetic radiations. And I hope you remember we did linear polarization, and we did circular polarization. And we saw how to express both of these in column vector form, or you just write them down as vectors anyways. So this is essentially a summary of what we did. So in principle what we've done is that so we've looked at solutions to the electric and magnetic wave equations, right? Basically to the equation del squared E is equal to 1 over c squared del 2 E by del t squared, and del squared B is equal to 1 over c squared del 2B by del t squared. So we've looked at solutions to these. And I hope that what we have is a good mental picture of the propagation of electromagnetic waves. We've seen that the magnitude of the B field is related to the magnitude of the electric field as 1 over C. This of course is true in vacuum. Yeah, in any other place जहाँ the refractive index is 1, which is equivalent to saying कि the relative permittivity is 1 and mu r is 1, right? Yeah, more generally this is equal to mod E over V. This is true generally, right, where V is the velocity of propagation in that medium. And I hope you all understand and appreciate now that for example, if my electromagnetic wave is propagating along this line, let's call this the z-axis, okay, then if we denote the electric field, let's say in red, then if the electric field is that sort of a sinusoid, right, then the magnetic field of course is oriented at 90 to that. It will be something like this, where this vector points in at 90 to the electric field vector, right? So for example, it's possible that if this is, let's say, the y-axis, then the magnetic field is probably pointing around the x-axis. I wrote mu, I meant y. So what we're doing is that we're slowly building up towards understanding physical electromagnetic waves in actual applications. And today's lecture will be a huge step forward for us. But then we'll build upon more in coming lectures. So here's what we want to do today. Essentially what we want to do is that consider an electromagnetic wave which is incident at a boundary between two mediums. What do we mean? Well, what we basically mean is that, you see, our wave equations let us solve for the electromagnetic wave in a particular medium. Let's say if something is generating an electromagnetic wave in that medium, yeah, what solution satisfied? लेकिन what if एक medium से दूसरे medium में आपकी waves travel कर रही हैं, फिर क्या होगा? For example, let's say ये अगर मेरा कोई interface है, और hypothetically, let's say कि our light electromagnetic wave comes here and then enters the second medium. Let's call this material A. Let's call this material B. In this lecture, what we want to understand is that what happens to electromagnetic waves when it travels from one medium to another. Now, we will make some assumptions. So, we'll assume that an electromagnetic wave goes from one material to another, but we'll assume that both materials are dielectrics. Once again, we assume this because we will do conducting materials after this, maybe probably next week in lecture 21 or 22. So, but for now, we are doing the relatively simpler case, but still a case which is very useful. So, once again, we're saying that both materials are dielectrics, and so both materials have no surface charge, and they have no free charge and no currents. Okay, no free currents either. But you see, you have some material A and you have some material B, and your electromagnetic wave is going from one material to the other. Okay. Now, the question is, what happens at the boundary? What happens at the boundary? Well, how do we know what happens at the boundary? Well, as you might have guessed, what we need are boundary conditions. Okay, what we need are boundary conditions. Boundary conditions for the electric and magnetic fields. So, do we have some such boundary conditions? Well, yes, we do. If you go to chapter 7, so if you go to chapter 7 in Griffiths, the chapter is called Electrodynamics. Then in that chapter, if you go to section 3.6, you can read up on all the boundary conditions, but I'll solve them here for you also, because I think it's really important that we understand this, because this is the core of everything that we'll do from now on. So well, our starting point for the boundary conditions is of course the Maxwell equation. So first I'll just write down the Maxwell equations once more. Okay, let's write down the Maxwell equations once again. Now I'll write them in integral form. Okay. Now we're inside a dielectric, so it's probably better to write down the Maxwell equation in terms of the displacement and in terms of the H vector. Now the first Maxwell equation we'll write is that we all know that the integral of the displacement, the surface integral of the displacement over some surface S is equal to the total amount of free charge encompassed in the region bounded that by surface. Okay, some surface S. The second Maxwell equation we'll write is that the surface integral of the B field over any area of any closed surface will always give you 0, and this is just an extension of the fact that the divergence of the B field is 0. The third Maxwell equation would be the extension of Faraday's law in integral form, and which is that the integral of E dot dl is equal to the rate of change of the integral of B dot dA. Okay. Now you might say कि यहाँ तो ये B dot dA का integral 0 हो गया था, यहाँ क्यों नहीं 0? ठीक है. So the answer to that question is that over here you're taking the integral over a closed surface, over here you're taking the integral over an open surface, which is bounded by this the loop which is defined over this line integral. ठीक है. अच्छा. And then the fourth Maxwell equation is that the line integral of H dot dl is equal to the free current I free plus d by dt of the integral over the surface bounded by the line integral of the displacement dot dA. Okay. So we will I'll use the same numbering when I refer to them in deriving my boundary conditions. So I will now derive my boundary conditions using these four Maxwell equations. Okay. And just remember this numbering. So this is so this would be equation 1, this would be equation 2, equation 3, equation 4. Okay. So let's first derive our first boundary condition. So let's call it boundary condition 1. Okay. Now if you refer back to the Maxwell equations, then using Maxwell equation 1, okay, we find that the perpendicular component, because let's say you're at an interface, okay, let's say you're at an interface and you then compute the surface integral across that interface. Okay. Let's say ये कोई interface है, कोई ये material A है, ये material B है. You make basically ये कुछ let's say surface level के interface की आप एक Gaussian pillbox बनाओगे ऊपर, and you'll subsequently make a Gaussian pillbox beneath. ठीक है. And you compute the surface integral of D over this volume. ठीक है. What that leads you to is that we'll call this material A and material 1, and let's call this material 2. Okay. So the surface integral, so basically the the orthogonal component of the displacement in material 1 minus the orthogonal component of the displacement in material 2 comes out to be equal to the surface charge density, the free surface charge density sigma f. Okay. But for a boundary between two dielectrics, ठीक है, sigma free जो है वो 0 है. So what we then find is that the displacement, the orthogonal component of the displacement in material A and material 1 is equal to the orthogonal component of the displacement in material 2. But we know that D is just nothing but the permittivity times the electric field. Okay? So what that tells us is that the permittivity in material 1 times the orthogonal component of the electric field in material 1 is equal to the permittivity in material 2 times the orthogonal component of the electric field in material 2. Okay? And I'll just make a box around this because this is our condition 1. Okay? Boundary condition 1. So let's now derive our second boundary condition. Now, for the second boundary condition, okay, we will use Maxwell equation 2. Okay? Use Maxwell equation 2. Okay? And what's Maxwell equation 2? It's just the surface integral of B dot dA is equal to 0. ठीक है? By the same logic, ठीक है, जैसे यहाँ surface integral की वजह से आपको right hand side sigma f मिला था, उस केस में 0 मिलेगा. So what you get is that the orthogonal component of B in material 1 minus the orthogonal component of B in material 2 is equal to 0. So what that then reduces to is that B1, the orthogonal component, is equal to B2 orthogonal component, and so this is condition 2. Okay? So we now have conditions for the orthogonal components of the electric and the magnetic fields whenever electric fields go from one dielectric to another dielectric. Okay? And the same would also hold for electric and magnetic waves. By the same convention and by the same logic, okay, we can then try to derive boundary condition 3. Now this time we use Maxwell equation 3. Okay? And if you use Maxwell equation 3, which is just that the line integral of E dot dl is equal to d by dt, the surface integral of B dot dA, what we find is that you make an Amperian loop between the two materials, and then you take the area enclosed by that loop to 0, then the condition we arrive at is that the parallel component of E1 minus the parallel component of E2 is equal to 0. So this gives us our third boundary condition is that E1 parallel is equal to E2 parallel, and this is our boundary condition 3. Okay? And similarly we can derive our boundary condition 4 using Maxwell equation 4, and in this case what you find is that H1L minus H2L so dot product ठीक है, is equal to the total free current enclosed in that region. Okay? But since we are considering a dielectric, so this is equal to 0. Okay? There are no free currents, no free charges. So what we find is that H1 parallel minus H2 parallel is equal to 0. And we know that H is equal to B over mu. And so what we get is that B1 parallel to what? Well, parallel to the surface, which is the interface between the material A and material 2. So B1 over mu1 is equal to B2 का parallel component over mu2. and this is our fourth and final boundary condition. So we now have 4 boundary conditions, and these 4 boundary conditions are very general, and they are always true for any dielectric interface as long as both materials are non-conducting and have no free charges on them. Okay. And so for example, these boundary conditions will work at you can imagine at air glass interface. These will work at you can imagine glass water interfaces, and for plastics, so on and so forth. So now that we have our 4 boundary conditions, we have all the tools we need to look at how light behaves at an interface between 2 materials. In this lecture, we'll do a simpler case, and in the next lecture, we'll do a more general case. So in this lecture, what we'll do is that we will look at reflection and transmission at normal incidence. What do we mean by normal incidence? Well, we mean that the propagation vector k and the and the surface normal are basically parallel to each other. So what we mean is that k and n hat are parallel, are collinear. Okay. So basically this is material A, this is material B, n hat is the surface normal at the interface. Okay. This vector k is the propagation vector, and they're essentially anti-parallel, parallel to each other. Achha. So let's draw this. Let's try and look at this pictorially, so that we have an idea of what we want to find. So this is the interface. Take care. Material A, material B. So let me first define my axes. So I'll just define my axis here on the left. So we'll take the vertical axis to be the positive z-axis. We'll take this to be the x-axis, and we'll take what's coming out of the plane of the page to be the y-axis. Over here, this is our k incident vector. Okay, it's coming towards the surface. Our electric field is of course orthogonal. So in blue here, this is the incident electric field. Okay, and our magnetic field is orthogonal to both the electric field and the k vector. And so this is B. So the symbol I here means this is B incident, this is E incident, this is the incident k vector. Okay. So similarly, some of the light will be transmitted. The amount of wave that is transmitted, so that'll be the transmitted k vector. So ठीक है, मैं the displays draw कर रहा हूँ ताकि space काफ़ी हो समझने के लिए, लेकिन this is a plane wave, so basically it's everywhere, right? Let me just emphasize. अच्छा है तो and so this is the, actually let me just draw this in a different color just to make it easier to follow. So the transmitted, this is kt, this is a vector, and similarly you will have some the electric field transmitted, and you will have some magnetic field which will be transmitted. And you will have some reflection from this interface, and we will draw the reflected part in yellow. So now the reflection k vector would point in the opposite direction to the incident k vector. So this is kr, this is the reflected k vector. This is ER, which is the reflected electric field, and this is BR, which is the reflected magnetic field. ठीक है, and this is a plane wave incidence. देखो, plane wave is everywhere, right? For a wave to be a truly plane wave, it extends basically from one corner of the universe to another, a true plane wave. So of course there are no real physical plane waves, but waves can be planar in with respect to the object they're incident on, and in this case we're assuming it's you get parallel plane wavefronts everywhere. Okay. So we're considering a plane wave. We have plane wave incidence, and this plane wave is polarized along the xy plane, and it's propagating along the z-axis. Okay. And we're doing normal incidence because it's easier than the more general case. Okay. So I hope that you understand the geometry of the problem here. Okay, because it's very important to understand this. Now our job would be to find these coefficients: B transmitted, E transmitted, B reflected, E reflected, so on and so forth. So we can express the incident electric and magnetic fields as the following plane waves. So the incident electric and magnetic fields can be written as E incident ZT is equal to E naught incident e to the I of kz minus omega t, because as I've already specified, the propagation is along the z direction and polarized along x. And so the corresponding magnetic field, these are of course vectors, of zt becomes equal to B naught incident, but B naught incident is just E naught incident over the velocity in medium 1, right? So this is v1, e to the I of kz minus omega t. Okay, and this is of course y hat. So the wave strikes the interface and we get some reflected and some transmitted electromagnetic waves. And the boundary conditions tell us what happens. So the the reflected EM waves will be the following. I'll write them in red. So the reflected waves would be ER vector of ZT will be equal to E naught R e to the I of kz minus omega t polarized along x. And this is where it gets really interesting. The B field, the B reflected of ZT will be equal to minus E naught over V1 e to the I of kz minus omega t y hat. I was trying to fit in the all the incident, reflected and transmitted on the same slide, but I don't think that's going to be possible, so we'll just use our space generously now. So it's really interesting where this minus sign comes from. So the minus sign here comes because of the fact that the propagation is now in the negative z direction. So actually there's a minus sign here, there's a minus sign here, right? Because the direction of propagation has now changed. So and this is still the original k vector, right? So and as a result of that, when you transform, this minus sign comes from Maxwell equation. Another way of thinking about this minus sign is that the pointing vector, which is E cross B, must point in the same direction as the direction of propagation. So the pointing vector, which we denote as S, must point in the direction of propagation. So this is E naught r. This is how the what the reflected waves look like. And finally, let's write down the transmitted wave. So the transmitted wave will be Et of zt is equal to E naught transmitted e to the I of kz minus omega t x hat, and the magnetic field that is transmitted will be E naught t over v2 e to the I of kz minus omega t y hat. Notice no minus sign here because well, the direction of propagation is the same. Okay, so now let's find E naught t, E naught r in terms of E naught I. Why are we interested in this? Because this will tell us how much light is transmitted and how much light is reflected. So another key point here is that notice that both the E and the B fields are in the plane of the interface. If you go back a couple of slides, you'll see that both electric and magnetic fields are in the plane of the interface. So they are parallel to the surface. So what we have to do, so basically that means that E perpendicular and B perpendicular are 0. So we only need to use the boundary conditions for parallel, the boundary conditions we had for E parallel and B parallel, so on and so forth. So our first boundary condition, if you remember, so this was boundary condition 3. We called it boundary condition 3, and this was that E1 parallel is equal to E2 parallel. Okay. So what is E1? E1 is the total electric field on the left hand side. Yeah, sorry, above the interface. So this is equal to E naught incident plus E naught reflected. Okay. And E2 is equal to E naught transmitted, obviously. So using this, what we get is that E naught incident plus E naught reflected is equal to E naught transmitted. Okay. This is the first of two simultaneous equations that we'll construct. The other one we will construct using boundary condition number 4. Which was that the parallel component of B1 or mu1 is equal to the parallel component of B2 over mu2. So the parallel component of B1 in material 1, before the light strikes the interface, the total parallel component is equal to E naught incident over V1 minus E naught incident over V1. Reflected over V1. Similarly, the parallel component of the magnetic field in material 2 is equal to E naught transmitted over V2. And so this gives us another equation, which is that 1 over mu1 times E naught incident over V1 minus E naught reflected over V1 is equal to 1 over mu 2 times V2 E naught transmitted. Okay, so this is our second equation. So what we then have to do is that we can simplify the second equation a bit to basically get that E naught I minus E naught R is equal to mu1 over mu2 times V1 over V2 times E naught T. And we can call this factor beta, where beta is basically equal to mu1 over mu2 V1 over V2. So in summary then, this condition is that E naught I minus E naught R is equal to beta times E naught T. So this is another way of writing the second condition we derived. So we have two simultaneous equations, and what we're going to try to do is to solve these two simultaneous equations and basically solve for the transmitted and reflected intensities. So so if we make E naught R the subject of the formula, then we know that E naught R is equal to E naught I minus beta E naught T. Okay, and if you substitute this into equation 1, then what you basically get is that so equation 1, if you go back, was that E naught R is E naught T minus E naught I. So if you substitute this for E naught R, so what we get is that E naught I minus beta E naught T is equal to E naught T minus E naught capital I. So 2 E naught I, if you just rearrange, it becomes equal to E naught T times 1 plus beta. So if you simplify this a bit more and make E naught T the subject of the formula, so E naught T becomes equal to 2 over 1 plus beta times E naught I. And this is a very, very useful equation because it tells us the magnitude of E naught T in terms of E naught I. But of course, we'd simplify this a bit more. But first, similarly, we can find E naught R. We know that E naught T is equal to E naught I minus E naught R over beta, right? And we also know that E naught T is equal to E naught I minus E naught I. So if we just substitute, then we get that the incident E field minus the reflected E field is equal to beta times the incident E field minus beta times the reflected E field. So the reflected E field becomes equal to 1 minus beta over 1 plus beta times E naught I. So that's the relative magnitude of E naught I. And so let's call this equation B, and let's call this equation A. Okay, so equation A and equation B basically tell us how to find the relative E field, knowing the initial E field that's coming in. So let's try to summarize these a bit more. So we have the reflected and transmitted components now. Beta जो है, beta is, let's just simplify this a bit. So it's mu1 v1 over mu2 v2. Now for most materials, mu1 is approximately equal to mu2. And we also know that the ratio of the velocities v1 over v2 is equal to the ratios of the refractive indices in those media, right? We know this from the wave equation. So beta is approximately equal to n2 over n1. So under the simplification, we can basically see that if you take equation B and if you substitute this new beta, then E naught R becomes equal to 1 minus n2 over n1 over 1 plus n2 over n1, okay, times E naught I. So E naught R becomes equal to let's see, so n1 will cancel, so you get n1 minus n2 over n1 plus n2 into E naught I. So now we know the reflected coefficient of the electric field in terms of the refractive indices. Okay, and just go back 3 slides, make sure you understand what this factor is, right? This factor is the reflected like this is the coefficient, yeah, which is multiplied by the exponent of kz minus omega t. And similarly, we can express the transmitted component. So then taking equation A, substitute beta is equal to n2 over n1, right? And what you basically find then is that E naught transmitted is equal to 2 over 1 plus n2 over n1 times E naught I, which is equal to 2 n1 over n1 plus n2 times E naught I. So E naught t is equal to 2 n1 over n1 plus n2 times E naught I. Now in the next lecture, we will derive what we'll call the Fresnel equations for reflection of light at dielectric interfaces. What we have derived here are basically those Fresnel equations for the special case of normal incidence. And so this equation for E naught here and the equation we had earlier for E naught R, this tells us everything that we need to know about how light reflects from a medium. Now, how light reflects when it goes from one medium to another. Now, there's some very interesting stuff that happens in the case of reflection. So I'll label this as an important note. So consider E naught R, which is equal to n1 minus n2 over n1 plus n2 into E naught I, which is the incident electric field. Now notice that you have to pay attention to this. So if n1 is greater than n2, ठीक है, यानी कि if the refractive index of material 1 is greater than the refractive index of material 2, then ER is in phase with EI because you have a positive sign. But at the same time, if N1 is less than N2, okay, if N1 is less than N2, then the reflected wave is 180 degrees out of phase, right? And we have a minus sign. So in other words, when V2 is less than V1, for example, light which is, let's say, going from air into glass, yeah, from air to a mirror or whatever. So on an air glass boundary, then the reflected light is 180 degrees out of phase. Now, I'll be honest with you, even at a personal level, whenever working with a physical photonic system, whenever we have reflections, sometimes even I get confused as to whether the reflected light is in phase, is shifted by 180 with regards to the incoming light. And so basically, whenever you have light going from a medium of lower refractive index into a medium of high refractive index, you always get some reflections. And those reflections are 180 degrees out of phase if the second refractive index is in fact higher than the first refractive index. So conceptually, these are two very, very important results. And I'll hope that they'll stay with you even after we're done with the course. There are many such results actually that I hope they'll stay with you after we're done with the course. So moving on then, let's see what happens to the intensities. So we know that the Poynting vector S is given as 1 over mu times E cross B. Okay. The Poynting vector, we discussed this in detail, and basically this is the energy transported per unit area per unit time, right? And in the last lecture, we actually discussed what's called the intensity, and we defined this to be the average of the Poynting vector over one cycle. Okay. And for a plane wave, we derive this to be 1 over 2 the permittivity of the medium times the velocity of electromagnetic waves in that medium times E naught squared. Okay. So so that's the intensity of light. Now let's define two constants. We'll define a constant called reflectivity, we'll call it R, and we'll call transmissivity, call it T. ठीक है, और reflectivity जो है हम इसको define करेंगे as the ratio of the intensity of light that is reflected over the intensity of light that was incident. ठीक है, and similarly we will define transmissivity as the intensity of light that is transmitted over the intensity of electromagnetic waves that were incident. ठीक है. Now I हमें पता है is given by this formula, which is EV E naught squared. Now reflectivity of course is easy, or R is equal to IR over II. That just becomes equal to, the factors of this becomes equal to 1 over 2 epsilon v E naught r squared over 1 over 2 E1 V1 E1 V1 E naught I squared. So that's just equal to E naught over E naught I squared. Okay, but from definition, R becomes equal to N1 minus N2 over N1 plus N2 squared, which is an extremely cool result if you think about it. Similarly, the transmissivity T becomes equal to IT over I incident. Okay. Now this is equal to 1 over 2 of E2 V2 E naught T squared over 1 over 2 E1 V1 E naught I squared. So of course, in general, E2 and E1 are not the same, V2 and V1 are not the same, and so this becomes equal to E2 V2 over E1 V1 times E naught T over E naught I squared. So substituting in for E naught T over E naught I, what we get is that so T then becomes equal to so we know that N is equal to the square root of the permittivity times the permeability, but we've taken the permeability for both materials to be, so let's say N1 is that, so the permeability is approximately equal to mu naught. Okay, the same would go for material 2, so mu1 and mu2 are almost the same, and so the only difference is because of the permittivities. So we can then write T as, so E2 over E1 basically becomes a ratio of N2 squared over N1 squared, and of course the higher the velocity, the lower the refractive index. So the velocity and the refractive index are inversely proportional. So V2 over V1 actually becomes N1 over N2, right? This is I hope this all makes sense because it's correct. And of course this is multiplied by E naught T over E naught I squared, which becomes equal to N2 over N1 times, so E naught T over E naught I, this becomes equal square of this times 4N1 squared over N1 plus N2 squared. So to summarize then, T becomes equal to 4N1 N2 over N1 plus N2 whole squared, and at the same time R becomes equal to N1 minus N2 over N1 plus N2 squared, right? So now what we get is the so what we have is we have the reflected and transmitted intensity ratio, right? And what I want you to do now is that I want you to check that the reflectivity T plus R is equal to 1, okay, which must be the case because of energy conservation. So now what I want you to do is take some test cases, and we'll do some problems on this also. That let's say you have a material with refractive index n1, you have a material with refractive index n2, and you have electromagnetic waves that are incident, and then some of those are transmitted and some of those are reflected, right? EI, ET, ET, and of course corresponding to the electric field is always a magnetic field also. And of course, if you go back, the Poynting vectors basically accommodate for both electric and magnetic field, right? Anyways, so now what we know is that for different values of n and for different values of n1 and n2, you get different transmission and reflection factors. Now, if you can imagine, okay, for let's say if you have light flowing down an optic fiber, okay, let's say this is optic fiber 1, and let's say this is optic fiber 2. Now when light goes from optic fiber 2 into optic fiber 1, this is the interface, right? So some of the light will be reflected back, some of the light will be transmitted, okay? So now if you're an optical engineer, if you're a design engineer, now you care about the refractive index of n1 and you care about the refractive index of n2, because if the refractive indices are very different from each other, then you get large amounts of reflection. I mean, if you look at the reflection coefficient at the top of the slide here, if n1 minus n2 is 0, then R is basically 0, so all of the light is actually transmitted. And so what you get is 4 over 2 square, which is just 1. But if n1 and n2 are very different from one another, then you get significant amount of reflection and very little transmissions, right? And this will tie into the concept of impedance matching afterwards. So I hope that all of this is clear. Now next time we'll have to grind through quite a similar but yet even actually more involved analysis. And next time we'll actually go towards light, EM waves incident at angles other than normal incidence. So at a general angle of incidence, right? So this we'll do next time. Plus we'll also derive some very interesting fundamental laws of geometric optics, which I'm sure you're familiar with, but we'll still derive them for the first time. So I hope that everything in this lecture has been clear. Most of the stuff that we covered was in Griffith's chapter. Basically, it's the chapter on electromagnetic waves, and the section is basically 3.1, 3.2. And next time we'll actually spend a significant amount of time on section 3.3, when we look at reflection and transmission at oblique incidence. Thank you very much for listening, and we'll see you next time. Thank you.